Hello and welcome to another episode of EnVisioneering Exchange, the podcast where industry leaders discuss the most important topics in sustainability, climate change, buildings, and urban efficiency. I'm Vic Marinich from Danfoss, and I'm delighted to be the host of this podcast. You can subscribe to our show on Apple Podcasts, Spotify, Captivate, or wherever you get your podcasts. Today we have Nick Mislak, Regional Segment Marketing Director for HVAC at Danfoss, here to talk about vapor and liquid injection compressor technologies and how market trends are influencing their adoption. Nick, thanks for taking time to join the show.
Yeah, thanks, Vic. I appreciate it. I'm interested to talk about this topic as heat pumps are a growing area. It's a hot topic for sure, and especially as we expand now into colder climates where these technologies are really needed to make units operate. I think the timing is just right to dive into it a bit more.
Before we take that deep dive into compressor injection, maybe let's take a little bit of a step back on the design side and let's talk about economizing in general. And I know for some people out there, depending on, kind of what you work with, you may be used to air side economizing, water side economizing, refrigerant side economizing. So let's just lay the foundation here, Nick. Which economizing are we talking about here? What does that application look like and kind of what components are needed?
The first question is, what is an economizer, right? It's a word, but nobody really gets into the meaning of what it is. But economizer is really just the device to increase the energy efficiency of a piece of equipment or a system, basically. So that's kind of the overarching, definition of economizer. And as you said, there's a lot of different types, right? There's water to air, so basically you're using air to cool water. There's air to air. So think of that as something like for a rooftop or a DOAS unit where you're bringing in maybe colder air to, give the cooling system a break or introducing more fresh air into the system to increase the efficiency a little bit. So there's two types there, but really the type we're going to talk about today is the refrigerant side. So refrigerant coming in, refrigerant going out, and that's where we're going to talk about, the portion of the economizer today as it pertains to vapor injection specifically.
With the economizer itself, right? So we're talking about, and I always hate kind of trying to talk through a schematic on a podcast, right? It's easier to draw stuff, right? But we're taking the refrigerant just after the condenser. Is that right? And we're bringing it into the economizer?
Yeah, exactly right. So on the refrigerant side, we're going to take liquid coming out of the economizer. There's a couple different ways to do it when we talk about vapor injection. Well, if you get into the components a bit more, so, a typical vapor injection economizer, you would have, of course, your economizer, which would be in this case a braze plate heat exchanger or microplate heat exchanger. You would have an expansion valve. You would have pressure and temperature sensors. And then, of course, some interconnecting piping. And then you may have, a solenoid valve for shutoff as well. But as you mentioned, so basically we're taking the feed coming out of the economizer or coming out of the condenser, going to the economizer. And there's kind of two different configurations, and they each have kind of drawbacks. One is what we call an upstream configuration, and the other is a downstream configuration. So, and that really just applies on where you take that feed coming out of the condenser. So if we're talking about a downstream configuration, basically then the whole portion of the condenser would go through your economizers. All the liquid coming out of your condenser first goes into your economizer, and then you do your economizing essentially. If you have an upstream configuration, then only a fraction of the liquid coming out of the condenser would go to your economizer. So there's a trade-off there in how you size your components. The downstream configuration can be a little bit more stable because you can maintain a better subcooling. But the upstream configuration, sometimes you can get away with a slightly differently designed heat exchanger, or maybe you need to add a couple of plates here to make up for the difference in subcooling. So there's some drawbacks there for sure, but there's kind of two different, overarching methodologies to do it. As you mentioned, it's a lot easier to show in a schematic, but those are kind of the two ways to do it.
Right. But it's, I think, important to note, right? I mean, we're adding a third heat exchanger to the system. Typically, we think of condensers and evaporators in your typical refrigeration system. Here, we're adding an intermediate heat exchanger right after the condenser. So that liquid is coming in, and then it'll be subcooled. And then part of that subcooled liquid then feeds back to the other side of the heat exchanger and evaporates, and then that's injected into the compressor, and we'll go into details there. But I know when I first saw those designs, my immediate thought was, oh, great, you're doing all this extra subcooling, and that's where your efficiency gain comes from, right?
Right.
And you do get some from the subcooling, but that's really not where the efficiency gain in your system comes from. And that's why I think it's important, right? We talk about the injection side of things coming up here next, right? Because that really is the key to getting the efficiency in an economized system, right?
Yeah, exactly. As you mentioned too, I mean, an easy way to think about an economizer in this kind of system is kind of as a mini evaporator, basically, right? Because it's set up almost the same way as an evaporator is set up for a chiller type system, for example. A lot of people are, of course, more familiar with that, but Yeah, as you mentioned, I mean, it really depends how you set it up. I mean, with vapor, kind of the main reason to get it, other than the expansion of the compressor operating map, right, is you do get the efficiency benefit, and you get a little bit more capacity as well. And the reason that is as you mentioned, as you subcool the liquid further coming out of the economizer, then your quality basically going into your evaporator is lower, right? So you get more benefit there as far as the capacity goes. But on the efficiency side of it, as you're injecting this kind of intermediate pressure, vapor into the compressor, you have, of course, your low pressure and then your high pressure, which is standard on every compressor. They have that, but when you have the intermediate portion, then you actually can adjust the compression. The compression ratio of the compressor actually changes, and you get a little bit more efficiency as well. And then also comes with the ability, of course, to cool the motor down and expand the operating map of the compressor to run at all these super low temperatures.
Right. Maybe the next big picture question, why are we all of a sudden talking about this, right? This isn't a new concept. I mean, economizing has been used, I guess mainly I remember from like supermarket days forever and ever, right? This is nothing new, but suddenly this is becoming much more popular. Why is it that this is becoming a lot more popular these days?
It's been around forever, right? Refrigeration, they've used it forever on low temperature systems, particularly with R22 and some of the other refrigerants that tend to run really, really hot. The compressors need to be cooled down. It's not new there. It's not new on the chiller side where they add, economizers in even for units that just do cooling only to get a little bit of a COP boost. So it's not new there, but it's new kind of in our world now because without having, vapor injection, we can't run down with a typical scroll compressor. We can't run down to really low evaporating temperatures, which means we can't have heat pumps run in really cold climates, essentially. That's kind of the reason why it's needed. Without it, you can have a reversible unit and it can run down in moderately cold climate zones. Maybe somewhere from, the north of the US down south, okay, heat pumps are okay to run there on a standard compressor. But as you go north and, you go into some of the colder ASHRAE climate zones, you really can't use a heat pump there without some other source of backup heat. With electric heat or hydronic or whatever, gas heat. You have to have some other heat to be able to kick on when the heat pump's no longer able to meet the demand. But when you add vapor injection, now our compressor map is so wide that we can cover almost the entire portion of the United States in most cases, in some cases even into Canada, without needing a secondary heat source. So that's really the benefit there. And when we do that, of course, we're not burning any fossil fuels, energy efficiency is increased, the decarbonization goals are kind of intact. That's kind of really the main draw there. As we see the heat pump adoption growing, we see it expanding into, more northerly climates.
Right. Okay. Gotcha. So we're talking about getting heat pumps moving further and further north. So that's why we're economizing in general. But now let's take a bit deeper dive into the injection part itself. So first, I think it probably goes without saying, you don't just take a standard off-the-shelf compressor and then tap it and think you can do injection. But so we need, I assume, a special compressor. And then you've mentioned both vapor and liquid injection technologies. Can you kind of talk about how both of those work and what's the difference between them?
So in the first question, yeah, as you said, I mean, it's not an off-the-shelf compressor, right? It's if you look at your standard scroll compressor, you have a discharge port and a suction port. But if you look at a compressor with injection, now you have a third port, which is your injection, your injection inlet essentially. So the compressor is designed and the internals of the compressor designed to be able to achieve that wide map. Basically, the injection line kind of goes piped up to the middle portion of the scroll set. And that's kind of where the injection occurs, basically, for compressors that have vapor and liquid injection as well. It's a purposely designed compressor for that application, basically. It's not an off-the-shelf, you can't take a compressor and modify it. It has to already be, designed for injection from the get-go, basically. So when we talk a little about liquid injection, is also, as you mentioned, has been around for a long time too. And it has some benefits, some drawbacks there as well. But one of the main benefits with liquid injection is you kind of do a similar principle. You're taking a line off the condenser coil and you have some sort of expansion valve or something like that that's modulating the liquid flow into the compressor. And then you have some feedback. You have a feedback loop based on your discharge gas temperature. So you have a probe that's mounted on your compressor discharge line. And then you have, a controller essentially that's reading the temperature and adjusting the valve based on the conditions. And really the way the liquid injection works is when that temperature of that discharge line gets too hot, then the valve opens and starts pulsing the liquid in to basically cool the compressor down so you don't cook the oil, the bearings don't get burned out, the paint doesn't start to melt off the compressor shell, things like that. But the liquid injection, its difference there basically is that you don't get the same benefits with vapor injection. You don't get the system efficiency improvements because you don't have the secondary heat exchanger in there, and you don't get any boosting capacities. It's a simpler system in terms of its architecture because you don't need those extra components. But as we see the market moving now, I mean, energy efficiency, that's always going to continue to progress. You just get more benefits out of vapor injection. So we're seeing kind of a move away from traditional liquid-only injection compressors into vapor injection.
I always get nervous when you talk about injecting liquid into a compression area, right? Liquid doesn't like to compress very well. That always made me nervous. So good to see the vapor one coming along. But you kind of touched on it, right? So liquid injection, then we're not really, let's say, optimizing the efficiency and the operating of the envelope, right? Liquid injection is more maybe, we can go maybe protection, or we do extend the operating envelope a bit because we can help bring down discharge temperatures and stuff. But it's really the vapor injection that has allowed us to really increase the operating envelope, increase the range the systems can work within. Is that right?
Yeah, the liquid injection, you don't really get, really the only benefit there is that you're able to extend the map, as you said. So the map is good from the perspective that it can run in, colder climates now, has lower evaporating temperatures. It can meet the needs of cold climate heat pumps in most aspects, but you lose all the benefits from efficiency and capacity that you get with vapor injection. So it's really just about, system reliability for liquid injection. It is a simpler system. It's a bit more plug and play. A lot of OEMs choose that method because it's an easier path to market as a first initial concept. But most people are kind of moving away of the vapor injection nowadays.
You hit on a point there, I think, about simplicity and design and so on. So if we talk on residential, there's 10 million plus or minus units a year, right? Maybe 4 to 5 of those are heat pumps already. And rooftops, it's probably, 20% are heat pumps, and we're seeing reversible chillers. So heat pumps are nothing new, but maybe going cold climate is, and economizing is, and injection is. So what specific design considerations do you have to take into account if you're going to design a system with not just a heat pump, but with an economizer and injection system to be able to reach all those low ambience or high temps?
The first step is, okay, we know what kind of unit it is, and what's the capacity of the unit? What do we need to meet, basically? So, it has to start with the compressor, right? Because we have to pick the compressor that delivers the desired capacity at whatever rating condition that the customer is trying to meet, essentially. There's some standard rating points for heat pumps that, OEMs, build their units based off of. And then, of course, there's other outlying points, to really cold climates. They want to run, really high temperatures at, minus 30 degrees Fahrenheit. So there's a lot of different points there. And it's really about finding first the compressor that can balance all those different points as far as the unit design goes. That's kind of the first step, right? Is to pick the compressor that meets the unit capacity. That's the heart of the system, basically, right? So,
and you mentioned by doing the injection, in essence, that compressor is going to be able to do more capacity than it would have been without it, right? I think that's one way you get the efficiency. You can take whatever, a 4-ton compressor and maybe get 4.5 tons with injection. So you're using a smaller motor, right, to get larger capacity, which obviously helps your COP.
Yeah, it's a bit more tricky than it is in previous times where you had a non-injection compressor, because in more simple times you had just a standard, 10-term set of polynomials, and you could run the simulations based off the HRI standards, and then, okay, here's your capacity here. But with the compressors with vapor injection, now you have extra, call them variables, that you need to consider, like injection temperature and SST, saturated discharge temperature, things like that, that really you need those inputs to kind of characterize how the system is going to perform at these off rating conditions. So it's a more complicated process to pick the compressor, and also to do simulations and the other individual component selections, because you're looking at, a lot more operational points than you would be in the past.
And I guess the superheat software that you would use, say, feeding an expansion valve into an evaporator, you're not going to want to use that same algorithm to feed it into your compressor, right? Because you're looking really to optimize two different things there.
You're still going to have a superheat valve and an algorithm, but for sure it's going to be tweaked for the liquid injection only. And kind of the other play of that too is that when we talk about vapor injection, we're talking about not necessarily just vapor, right? Because the same compressor can do vapor, could do liquid, or could do a wet injection, which is a combination of vapor and of wet, of liquid essentially. So the controller needs to be able to decide when to move into those different regions, basically. And it does that based off of superheat, of course, as you mentioned on the algorithm, but then also feedback from, discharge gas temperature sensors, things like that. Basically, as the temperature increases and the compressor discharge gets too hot, then it has to figure out the switch modes and how much to open the valve to cool the compressor down to maintain, system performance and all that kind of stuff. It's a lot more complicated, as you mentioned, than just, a standard superheat controller that we're all familiar with today.
Right. Kind of called it a mini evaporator, but it's definitely a lot more complicated control than your standard evaporator on a rooftop or chiller unit, right?
Exactly. Yeah. Yeah. You definitely need a bit more feedback there than just a standard, valve driver. In this case, it's really suited for electronic valves in this case more so than a mechanical TXV, just because you need that kind of quick real time feedback that you get with an electronic valve that you don't necessarily have with a standard thermostatic valve.
Now, what about putting a TXV on the main evaporator? Is that still doable?
Yeah, it's still okay. Of course, there's some drawbacks there. I mean, if it's a variable speed system, the compressor's very mass flow all the time, things like that, then for sure EEV is still going to be the best way to go as far as performance and system stability and operation at all the different points that the unit runs at. But if it's a kind of a more simple system with fixed speed compressors, then yeah, TXV is still fine in a lot of cases.
Are injection systems available both with a fixed speed and variable speed compressors?
Yeah, so everything kind of started, of course, with fixed speed. Fixed speed compressors, single compressors, and then you can, of course, do tandems or trios to size up the system and capacity. So that's kind of where it all began for us and also other manufacturers as well. But what we're seeing now is a lot of push to variable speed compressors, particularly for a lot of units that like DOAS units and things like that, where they mostly use variable speed compressors as kind of the heart of their system. But then they want to move into cold climate heat pumps. So that's kind of where the vapor injection variable speed compressor comes into play. It's not one or the other. A lot of times you'll have maybe one circuit that's variable speed, one that's fixed speed, and then it really just depends on how the unit's configured and what the end goals are from the manufacturer there. But yeah, for sure, both technologies are in play and growing.
So listeners to this podcast will know we've spent a lot of time in the past talking about heat pumps and how they operate in colder climates, and talked about the U.S. Cold Climate Heat Pump Challenge. So given the new technology of injection, vapor injection, where do cold climate heat pump developments stand now? How are we looking in the marketplace?
We're still growing. I mean, there's still a huge initiative there for cold climate heat pumps. I mean, not only on the kind of the federal level, sponsored from the heat pump challenges, but of course, that's all the universities are working on projects, of course, that are funded. Certain municipalities, California, other states where they have either natural gas bans kind of either already put in place or ones that are going to be coming in the near future. So of course that's going to spur more development because consumers are going to need some other technology basically if they can't go to a gas furnace in those geographic areas. So it's going to continue to grow, I believe, as the time goes on, and particularly if we see increases in oil and gas prices, things like that, and that'll of course maybe drive more energy efficiency units, things like that. So I think the adoption level is going to continue to get boosted as time goes on.
And are these cold climate heat pumps, are they available on the market today from some OEMs?
Yeah, so on the residential side, as you mentioned, I mean, there's a lot of kind of the major OEMs that already have released products for cold climate heat pumps. And that's kind of where it all began. Start small and then grow big. So what we see now is a lot of companies that are make larger rooftops, dedicated heat pumps, things like that, where they're a lot larger capacities. They're kind of growing in the space right now. But for sure for residential, I mean, you can buy units off the shelf. In the past, there was rebates and things that were available for it to kind of spur on the heat pump adoption even more. So that's another factor that can make heat pumps grow, of course, a little bit faster. But yeah, definitely, it's moving up in the unit capacity size as well.
Okay, great. So maybe there are still some OEMs out there who haven't transitioned into a product range that's using liquid or vapor injection. How can Danfoss or other suppliers work effectively with those OEMs to kind of help expand the use of liquid and vapor injection?
Yeah, I mean, one thing that's great about Danfoss, of course, but we have the application experience as well. We have a lot of really talented people that know the engineering side, and that's all fine and good. But one thing is that we can offer that some other suppliers can't is the full product portfolio. So where some of their customer or some of their suppliers may just be able to offer a valve or just a compressor, we're able to offer the compressor, the heat exchanger, the valve, the sensors, basically everything that you would need to do to build the system. And in fact, we have a guideline put together where we have, if you use this compressor, then these are the components that you use to build the system. So it's kind of, we've made it almost as intuitive as we can from a manufacturer to be able to just say to the OEM, okay, here's your solution. These are the components that you need to build it. And then we're there to provide them, of course, support if they need qualification or any engineering support that they need to kind of help them through the process. So I think that's where we're able to build a lot of value there for Danfoss.
Mm-hmm. So we've talked now a good bit on economizing and vapor injection. It sounds like it's kind of a win-win for some incremental components. We're getting higher efficiencies, higher heating temperatures, operating down at lower ambience. Where else can this technology be used? If we look besides heat pumps, then I have to imagine there's other opportunities in the refrigeration cycle where we can use economizing. How do you see that moving forward in the future?
I think the main area of growth here, because we've been, we talk about, vapor injection a lot in kind of the comfort cooling sense for building occupants or, houses, stuff like that. But I think one benefit I see in that in growing and what we see in the market as well is that buildings need hot water. There's a lot of existing systems that have boilers and things like that where they're getting old and, there's efficiency increases there and they want to transition to a different technology. So that's kind of where I see this playing in more on the heat pump side there's other markets that traditionally haven't been served well by heat pumps because the technology hasn't been ready and haven't been able to produce, say 200 degrees, Fahrenheit leaving water that's needed for, baseboard heat where, that's kind of been the standard. But with the new compressor technologies and all this additional vapor injection, things like that we can do, then we're able to kind of play in that space now. So that's, one area that I think heat pumps could have pretty good growth going in the future. Again, there we could have, a trade-off where you have, some hybrid systems where you have first stage heat pump, second stage boiler. You can get a lot more energy efficient system by kind of combining different technologies where, it suits the application space basically. So I think that's kind of where I think things are going to go. We've seen it at the shows, every year we see more heat pump water heaters. 10 years ago, that wasn't really a big thing, but now it's becoming pretty widespread in the market. So I think we'll see that in kind of the rest of that, space as well.
So we've talked a bunch on the heating side. What about stretching the operating envelope the other way in like high ambient? I mean, we have a climate change and we're seeing temperatures get hotter and hotter, and especially if we talk the Middle East. I mean, we see Dubai, Saudi. I mean, the construction industry there is still booming. Can we use injection to help get better efficiency at those super high ambient temperatures as well?
Yeah, you can. So, that's a good point. So we've been talking about it just on the heating side, but the injection's not only at really cold climates, low evaporating temperatures, right? There's still benefits at just normal operating conditions and also higher, saturated suction temperatures. You can still get benefit there, even in cooling. A lot of times if it's a unit that's already designed, maybe they add vapor injection to it and maybe their ER goes up a little bit or their IER goes up a little bit. So there's some benefits there. And we talk about maybe data center space where they don't really care so much about cold climates, but they need those high saturated suction temperatures. Then maybe we're able to move the operation a little bit to the right-hand side of the compressor map, since we can now add injection or liquid injection to cool the compressor down. So I think there's some flexibility to kind of play in some of those spaces as well, for sure.
Mm-hmm. Okay, great. I think that was all the questions I have. Is there something I forgot to ask you, Nick, or anything you want to wrap up with?
No, that was it. I appreciate the time, Vic. It was great having a talk with you today. It's a good topic to discuss. I'm always happy to go over it. I appreciate it.
So then that's it for this episode of EnVisioneering Exchange, and I'd like to thank my guest, Nick Mislak from Danfoss, for joining us.
Yeah, thank you, Vic.
Don't forget to subscribe to EnVisioneering Exchange on Apple Podcasts, Spotify, Captivate, or wherever you listen to podcasts. Lastly, if you enjoyed this episode, don't forget to rate, review, and share with your network. Thanks for listening, and talk to you next time.
This podcast is for information purposes only. The views, information, or opinions expressed during the EnVisioneering Exchange podcast series are solely those of the individuals involved and not necessarily represent those of Danfoss LLC and its employees. Danfoss LLC is not responsible and does not verify for accuracy any of the information contained in the podcast series available for listening on this site. This podcast series does not constitute professional advice or services. This podcast, including Danfoss LLC and the producers, disclaim responsibility from any possible adverse effects of information contained herein. Opinions of guests are their own, and Danfoss LLC in this podcast does not endorse or accept responsibility of statements made by guests. This podcast does not make any representations or warranties about the guest qualifications or credibility. Individuals on this podcast may have a direct or indirect financial interest in products or services referred to herein. This podcast is available for private, non-commercial use only. You may not edit, modify, or redistribute this podcast. The developers of the EnVisioneering Exchange podcast site assume no liability for any activities in connection with this podcast or for use of this podcast in connection with any other website, computer, or playing device.